Okay, the purpose of this video is to do a simple example of a feedback control system, mostly so you can get an understanding of the nomenclature in the previous video, and also just to give you a feeling for the sorts of things that happen in feedback control systems. Again, this is going to be a very simple example. Much more complex examples will probably follow. So in the previous video, we developed this transfer function, which basically tells us the relationship between the output of this feedback system and the input. And in this video, we'll do a much simpler system using these results and show you what we get. So the simpler system that we will do, is the following. I have a desired input. I compute an error. We'll show exactly what that is in just a minute. And I have a simple gain as my controller. I'll have a plant that basically has a transfer function 1 over s plus 1. This is a fairly pedestrian transfer function. It represents something that starts off and grows exponentially until it levels off at some steady state value. We'll have the output fed back directly into the subtractor. So this is the error, this is the input to the system. Okay, so by looking at this, hopefully you can see that my plant has a transfer function of 1 over s plus 1. The controller has a transfer function of just the gain k, and the sensor transfer function, since I have the output y directly fed back into the error, just has a transfer function of 1. Okay. With these values, the overall transfer function of this system, h of s, is equal to let's see, p of s, which is 1 over s plus 1, times gc of s, which is k, over 1 plus p of s, which is 1 over s plus 1, gc of s, which is k, and g sub s of s, which is 1. Okay. So to make this a little more straightforward, I will assume that everybody's okay with just multiplying by 1, and I'll multiply the top and bottom of this fraction by s plus 1. And when I do that, I get that this s plus 1 cancels this s plus 1, so I'm left with just k in the numerator. This s plus 1, this one right here, cancels this s plus 1, and this s plus 1 is multiplied by this 1 out here, so I get then s plus 1 plus k. I'll tidy up this fraction here just a little bit. So basically, what we have then is the transfer function is 1 over s plus 1 plus k. Okay. I'm sorry. K over s plus 1 plus k. Okay, so that's the transfer function from output to input. You can see if we now draw a pole zero plot of this transfer function, if this is the imaginary axis and this is the real axis, so this is imaginary and real, the pole that this transfer function has a single pole given by this 1 plus k here. And you'll remember the form of these expressions for poles is s minus the pole. So s plus 1 plus k means that there's a pole over here at a value of minus 1 minus k. Okay, so you can see that I've taken my original system, which had a pole at minus 1, and I've moved that pole to the left, assuming that k is positive. I've moved that pole to the left. What this implies then is that my original system had a transfer function or an impulse response that looked something like this. With the feedback, I'm able to make the impulse response look something like this. In other words, by moving this pole to the left, I've decreased the time that it takes for the system to respond to changes in the input. Okay, now again, that assumes that k is positive. What happens if k is negative? So we'll actually put here, this is k greater than 0. If k is negative, what happens here? Well, if k is more negative than negative 1, I can actually move my pole out here. So if k is less than negative 1, I've moved my pole out here, and this corresponds to a transfer function that looks like this. So by having a negative gain, what I've actually done is caused my system to become unstable, which is typically a bad thing. So this is probably the simplest example you can come up with of a feedback system, and you can observe how the gain changes the location of the single pole in the original system. Positive values of k make the pole move to the left. Negative values of k make the pole move to the right. And once that pole crosses the imaginary axis, then your system becomes unstable. One last comment, and then we'll be done. As I make the gain, as I make this gain k larger, then the input to the system u also becomes larger. So I might have a fairly small error. If I make k quite large, then the input u can also be quite large. Now, for some systems this is fine. For other systems this may be a problem. For most physical systems, you have some upper limits on either the amount of voltage or the amount of force or whatever the input to the system is. You may have upper limits on how big that can be. And by making the gain large, again, by making the gain large, we get this situation where the system responds quickly, but it responds quickly because the magnitude of the input has been made very large. And sometimes that may be a bad thing. It turns out that one of the real important parts of the art of developing control systems is to balance all the different things that you want to have happen. So you might want a system that responds quickly but that requires a fairly small input where possible. You can talk about things like rise time, overshoot, settling time. All of these things can be affected by the control system that you choose. And with that, we'll end this video.